A course in paleomagnetism. Hi and welcome to Geologic. My name is Asha. I'm a geologist living in Norway. On this channel I talk about anything geology related. This fall I've started a course in paleomagnetism. First episode was some weeks ago, so if you haven't seen it, I will link it down below. And we continue this series with a closer look at the ferromagnetic minerals. So grab a cup of your favorite drink and let's see what's in the cave today. When we apply a magnetic field, different materials respond in different ways. This response is due to the magnetic moment of atoms. The three main behaviors are diamagnetism, paramagnetism, and most important, ferromagnetism. Diamagnetism is a type of magnetic behavior where a material gets a tiny magnetization in the opposite direction when a magnetic field is applied. This magnetization disappears when the magnetic field is removed. For example, materials without any inherent magnetic moment, like quartz, only show diamagnetism. These materials have a negative magnetic susceptibility, meaning they slightly repel the magnetic fields, and this property doesn't change with temperature. Paramagnetism is a magnetic behavior where the materials with atoms that have magnetic moments get magnetized in the same direction as an applied magnetic field. This magnetization disappears when the field is removed. At temperature above absolute zero, thermal energy causes the atoms' magnetic moments to move randomly. Without a magnetic field, these moments cancel each other out, resulting in no overall magnetization. When a magnetic field is applied, it aligns the magnetic moments of the atoms, creating a net magnetization in the direction of the field. Ferromagnetism, on the other hand, is a magnetic behavior where the materials get strongly magnetized because the magnetic moments of their atoms interact and align with each other. They have a maximum level of magnetization called saturation magnetization. Beyond this point, increasing the magnetic field won't increase the magnetization. And as temperature increases, the magnetization decreases. At a certain temperature, called the Curie temperature, the material loses its ferromagnetic properties and becomes paramagnetic. Ferromagnetic materials can record the direction of an applied magnetic field even after the field is removed. This is due to a property called hysteresis. Atoms in ferromagnetic materials can have their magnetic moments aligned either parallel or anti-parallel to each other. This interaction is called exchanged coupling and is due to the quantum mechanical effects. When magnetic moments align in the same direction, the material is ferromagnetic. Anti-parallel coupling is when the magnetic moments align in the opposite direction, and it can lead to anti-ferromagnetism if they cancel each other out, or ferrimagnetism if they don't completely cancel out. But let's dive into some examples of minerals. There are two main series, titanomagetites and titatohematites. These minerals are primary phases in igneous rocks and usually make up 1% and 5% of the rock's volume. Titanomagetites are a type of magnetic mineral that are opaque and have a cubic crystal structure. They are made up of a mix between two end members, magnetite and ulvospinel. Magnetite is a mineral where the magnetic properties are strong. Its magnetic moments align along a specific direction in the crystal called the magnetocrystalline easy direction. It's the direction in a crystal where it's easier to magnetize the material. Ulvospinel is a mineral where titanium replaces some of the iron. Titanium doesn't have a magnetic moment, so as more titanium is added, the overall magnetization decreases. Ulvospinel is anti-ferromagnetic at low temperatures but become paramagnetic at room temperature. In short, titanomagetites are magnetic minerals whose properties depend on their iron and titanium content and their crystal structure. Titanohematites are magnetic minerals that are a bit more complex than titanomagetites. They are less common in most igneous rocks compared to titanomagetites, but can be dominant in highly silicic or highly oxidized igneous rocks and red sediments. Hematite, a common form of titanohematite. The magnetic moments of iron atoms in hematite are mostly aligned in the opposite direction, but not perfectly, leading to a weak net magnetization. This is counted anti-ferromagnetism. The temperature at which hematite loses its anti-ferromagnetic properties is 680 Celsius. Ilmenite is a magnetic mineral with a specific structure and properties. The magnetic moment of iron atoms in each layer align in the same direction, but alternate layers align in opposite directions, making ilmenite anti-ferromagnetic. Its Neal temperature, the temperature where it loses its anti-ferromagnetic properties, is 218 Celsius. So now we have gone through some of the minerals' behaviors and looked at some examples of minerals. We will just shortly touch upon some processes that can affect the minerals. These are exsolution, low temperature oxidation and deuteric oxidation. Exsolution is a process where certain minerals like titanomagetites and titanohematites separate into different regions when they cool down from high temperatures. At around 1300 Celsius, these minerals are mixed well. As they cool, they start to separate into titanium-rich and titanium-poor regions. The separation changes the magnetic properties of the minerals. It also breaks down large grains into small ones, affecting their overall structure and properties. In simple terms, exsolution is when a mineral unmixing itself into different parts as it cools, which changes its magnetic behavior and structure. Low temperature oxidation happens when minerals like titanomagetites react with oxygen at low temperatures, which will mean below 200 Celsius. This process can occur due to weathering at Earth's surface or hydrothermal changes. Magnetite can, for example, oxidize to become maghemite, which has a similar structure but different properties. Low temperature oxidation is like a slow rusting of minerals, changing their structure and magnetic behavior. Deuteric oxidation is a process that happens when igneous rocks cool down. As the rock cools, the iron, titanium, oxide minerals in it react with oxygen. This usually happens at around 750 Celsius and specific oxygen levels. The minerals change composition, becoming more iron-rich. This change affects their magnetic properties, making them more magnetic. The minerals also break down into smaller grains, which further affects their magnetic behavior. The extent of these changes depends on how fast the rocks cool and the oxygen level. So that's it for today. If you have any thoughts or questions, leave a comment down below. Tune in next week and have a rocky day. Of course.